Welcome to our calculus series. Today, we are going to explore a fascinating and powerful concept known as uniform continuity. If you have already studied regular continuity, you know it ensures a graph has no breaks or jumps. But uniform continuity takes this a step further. It provides a global guarantee about how a function behaves across its entire domain. Understanding this difference is crucial for advanced mathematics, physics, and computer science. Let us dive in and build our intuition from the ground up. To understand this topic, let us start with a simple driving analogy. Imagine you are driving a car along a perfectly straight highway. On this road, a tiny predictable adjustment of your steering wheel will always produce a small, safe change in your car's direction, no matter where you are on the highway. But now, imagine driving up an infinitely winding mountain road. At the bottom, that same small turn keeps you safe. But at the very top, where turns are sharper, it might send you off a cliff. Regular continuity just means the road has no missing bridges. Uniform continuity is like the straight highway. One safe steering rule works everywhere. Building on our driving analogy, let us look at how this translates to calculus. In standard continuity, you can keep a function's output within a tiny error margin called epsilon by keeping the input within a tiny window called delta. However, the size of this delta window usually changes depending on which specific point on the graph you are looking at. If the graph suddenly gets very steep, you need a much smaller window to stay safe. Uniform continuity changes the rules entirely. It demands a global standard rather than a local one. You must be able to find a single, universal delta window that works for every single point in the entire domain simultaneously. Now that we understand the global nature of this concept, let us look at its formal mathematical definition. Conceptually, this formula is just stating our highway rule. One steering tolerance works everywhere. Let us break down the symbols. Epsilon represents the maximum allowed error or distance between the output values on the y-axis. Delta represents the required closeness of the input values on the x-axis. The letter D stands for the domain, which is the entire set of valid inputs. The absolute value of x minus y is the horizontal distance, and the absolute value of f of x minus f of y is the vertical distance. The key here is the order. We pick delta based only on epsilon, and it must work for all x and y. To see exactly what this formula means, let us look at a visual representation. On the left side of this diagram, we have a straight line with a constant slope. Notice how a box of fixed width delta and height epsilon can slide anywhere along the line, and the function never escapes through the top or bottom. This is uniform continuity in action. On the right, we see a parabola. A box that works perfectly at the flat bottom fails completely at the top because the steep curve shoots out of the box before reaching the side boundaries. To fix this, you would need to shrink delta as you move right, which proves the parabola is not uniformly continuous. Before we move on to more complex functions, let us see this with a concrete example. We want to prove that the linear function f of x equals 3x plus 2 is uniformly continuous on the entire real number line. We are given an arbitrary error margin, epsilon, which is greater than 0. Our goal is to find a corresponding input window delta that depends only on epsilon and works for any 2 points, x and y. To do this, we will work backward from the conclusion we want to reach. We start by examining the distance between the outputs, hoping to reveal the distance between the inputs hidden inside it. Continuing with our proof, we begin by substituting the actual definition of our function into the output distance formula. This gives us the absolute value of 3x plus 2 minus the quantity 3y plus 2. Next, we distribute the negative sign to the second set of parentheses. The positive 2 and the negative 2 cancel each other out completely, removing the constant shift of the line. We are now left with just the absolute value of 3x minus 3y. Finally, we factor out the common multiplier of 3. Since 3 is positive, it pulls completely outside, leaving us with 3 times the exact input distance expression we were looking for. Now that we have simplified our expression, let us find our universal window. We set our simplified output distance, which is 3 times the absolute value of x minus y, to be strictly less than our error margin epsilon. To find out what restriction we need to place on the input distance, we simply divide both sides by 3. This isolates the input distance, showing it must be less than epsilon divided by 3. This final inequality tells us exactly how to choose a universal delta. Because setting delta to epsilon over 3 contains no x or y variables, it works everywhere on the real number line. Physically, this means our tolerance is globally stable. So, we have proven that a straight line holds up to uniform continuity. This brings us to an important question. What happens when a function fails this global test? As we saw in our earlier diagram, not all continuous functions are uniformly continuous. If a function represents a curve that gets steeper and steeper as you move away from the origin, it becomes impossible to pick a single universal delta for a given epsilon. The classic example of this is the squaring function, f of x equals x squared. Because its steepness constantly increases, any fixed tolerance window will eventually be broken. Let us prove mathematically why this failure happens. We want to show that f of x equals x squared is not uniformly continuous on the entire real number line. To prove this, we must show that the output distance can become massive even if the input distance is kept tiny. We start again by writing the distance between the outputs, substituting the squaring function to get the absolute value of x squared minus y squared. Using basic algebra, we factor this difference of squares into two separate absolute value terms multiplied together, the distance between inputs and the sum of the inputs. Continuing with our parabola, let us assume we try to pick a universal delta to control the input distance, keeping it smaller than this tiny value. We substitute this maximum input distance back into our factored equation to see what happens to the outputs. By replacing the input distance with our chosen delta, we get an approximation of the output distance, which is delta multiplied by the absolute value of x plus y. This new expression reveals the fatal flaw. The output distance is not just controlled by delta, it is multiplied by how far out on the number line we are looking. Now let us see the final result of this flaw. If we take the limit as our inputs move toward infinity, the sum of x and y grows without bound. We evaluate the limit as x approaches infinity for delta times the absolute value of x plus x, and the result is infinity. This means that no matter how incredibly tiny you make your universal delta, eventually the position term becomes so huge that it creates an output distance larger than any chosen epsilon. The curve becomes infinitely steep, making a single global tolerance window impossible. Physically, the system's sensitivity blows up. Now that we have seen the math, let us understand why this matters in the real world. In fields like computer science, engineering, and numerical analysis, we often approximate smooth, continuous curves with straight line segments to make calculations possible. If a function is uniformly continuous, a computer can safely use a fixed grid size or a universal sampling rate to map the function without missing any wild spikes. However, if the function is not uniformly continuous, the computer might sample the data at regular intervals and completely miss a massive sudden change because the curve got too steep between points. To wrap up our lecture, let us review the most important ideas we have covered today. First, remember that regular continuity only guarantees that a local error margin exists for each specific point, meaning sensitivity can grow out of control. Second, uniform continuity is a much stronger guarantee. A single fixed margin of error for the input will always keep the output within a desired target everywhere. Third, functions like parabolas that become infinitely steep will fail this global test. You have now mastered the foundation of uniform continuity, a concept that ensures global stability in advanced mathematics.